Hello everyone, my name is Azalia Mirhosseini and I'm a computer engineering PhD student at Rice University. I work at ACES lab under supervision of Professor Kushamfar. I am going to present my work on phase change memory performance optimization by data encoding. Phase change memory or PCM is an emerging non-volatile memory technology with promising properties. It works based on thermal mechanisms which alter the phase change material from amorphous to crystalline or vice versa to create 0 and 1 states of the memory. If we compare PCM to the currently prevalent memory types such as NAND flash and DRAM, we observe the following. PCM surpassed NAND flash due to its lower write energy and higher write endurance, and that it's bit programmable. PCM advantage over DRAM is that it's scalable and non-volatile. However, it still requires a much higher write energy compared to DRAM. To realize PCM potential as a next generation technology, improvements in its energy performance is required. A quick look at PCM energy characteristics shows us that its programming or set and reset requires very high currents. On the other hand, PCM reads are very efficient. Our approach improves energy performance by encoding data on PCM such that it exploits the efficient reads to reduce the amount of costly set and resets. Here is the overview of our coding scheme. We first divide the input stream of data that is going to be written on the memory into chunks of n-bit words. Thus, there are a total of 2 to the power n of such words. We call them W1 to W2 to the power n. We assign a number of codes or symbols to each word. Each time a new word is set to be written on a location of memory, we first read the data that currently exists on that location. In this picture, assume the new word is W1 and the existing data is C22. We choose the symbol of W1, which incurs the minimum overwrite cost for replacing C22. Assume that C1J is the symbol of W1 that causes this minimum overwrite cost. This means that a transition from C1J to C22 requires minimum number of set and resets compared to a transition from every other symbol of W1 to C22. Here I provide a sample example of encoding 2-bit word with 3-bit codes. In this case, each word has 2 symbols. Assume that A, B, C, and D are the words and we want to overwrite C by B. Data is encoded on the memory. Thus, for word C, either the code 101 is written on the memory, in which case we encode word B with its 001 symbol, since then the overwrite only needs a set. Or word C has been coded as 010 on the memory. In that case, we encode B with 110, since then the overwrite only requires a reset. Therefore, we have reduced the energy cost of direct overwrite of C by B from a set plus a reset to only a set or a reset. Now we go forward to formally define the coding problem. Assume that we encode n-bit words and we want to code them with n plus k-bit codes with the goal of minimizing the average overwrite cost on PCM. We prove the problem of finding the optimal codes is NP-hard. We provide 2 different solutions to solve this NP-hard problem. One is based on dynamic programming that finds the code suboptimally, and another method is based on integer linear programming that finds the codes optimally but has computational complexities for larger problem sizes. We extend our coding scheme to perform further optimizations for cases where the distribution of data is highly skewed. We also perform optimizations for multi-level cell PCM. A multi-level cell PCM stores many bits in one cell and has different energy behavior compared to the conventional PCM. We provide detailed coding schemes for such memories that best captures their properties to enhance memory energy performance. Our evaluations show significant improvements in PCM energy performance. More information and links to related papers are available on my website. Thank you for watching this video.